All right, so we're going to start by drawing an X and Y axis here, and then we're going to put the wave on here. So the wave is in red, and I've drawn one complete wave cycle. And so the height of that wave cycle, right, from the origin to the peak of the crest, that would be the amplitude. Now, that's not a term we're going to use an awful lot in this chapter, but just giving you a little extra information on waves here. The wavelength is technically the length of one complete cycle. So if we start there, where the first green dot is there on the left, and we end, right, the complete wave cycle ends at the other green dot on the right, that is technically the wavelength. Now, often the definition of wavelength is listed as the distance from the crest to the crest or the trough to the trough, but it can also be reported as the distance between corresponding points on a wave. I'm going to try to address several of these questions now. The relationship between frequency and wavelength is an inverse relationship. The relationship between frequency and energy is a direct relationship. And so number 4 kind of outlines those two equations. We know that wavelength times frequency is equal to the speed of light. And so that was, we're answering number 4 now. And so also we know that energy is equal to Planck's constant times frequency. Now, in terms of the speed of light, that's c. So c is equal to 3.00 times 10 to the 8th meters per second. And so it's important to take note of those units. Frequency, right, that's that funny looking V. That has units of hertz, which is the same thing as 1 over seconds, which is the same thing as seconds to the -1. Now, just to be consistent, I'm going to go back up here to the speed of light and put in seconds, because that's what I did in frequency. So conversion factors between meters and nanometers. Why would I have you do that? Well, often nanometers, that's the wavelengths are sometimes given in nanometers just to make the numbers a little easier to deal with, and you'll see why in a minute. We know that 1 meter is 10 to the 9th nanometers. So wavelengths can be pretty long or pretty short. And so sometimes they're given in nanometers just to make it an easier number to deal with. So I can either have 1 meter over 10 to the 9th nanometers, or I can flip that over 10 to the 9th nanometers per 1 meter. So in this problem, we're looking for frequency, and we're given wavelength. So that tells me we're going to use this equation, that the speed of light is equal to the wavelength times the frequency. So I know that the speed of light is 3.00 times 10 to the 8th meters per second. And I'm given the wavelength, so that's 4.10 times 10 to the -12 meters. And I'm solving that for frequency. So one thing I definitely want to point out to you guys is that the unit here in the speed of light, the distance unit in the speed of light, and the distance unit here in wavelength have to be the same. You must do some conversions if they're not the same already. So when I go ahead and do the algebra here, I get 3.00 times 10 to the 8th meters per second over 4.10 times 10 to the -12th meters. All right, that way my meters cancel out. And I will get 7.32 times 10 to the 19th. Per second, right? Or 7.32 times 10 to the 19th hertz. So this problem is very similar to the ones we've been doing, to the previous problem. And so we're again going to use the equation C equals wavelength times frequency, knowing that the speed of light is 3 times 10 to the 8th meters per second. We're looking for wavelength this time, and we know that the frequency is 6.01 times 10 to the 14th hertz. So when I solve that, I get that the wavelength is equal to 4.99 times 10 to the -7th meters. Now I know it's meters because that's the distance unit there, and the hertz and the per second on the left side canceled each other out. So we use Planck's constant to relate energy and frequency, and Planck's constant is given by an h. And it's got a very small value, 6.626 times 10 to the negative 34th. And the units are a little interesting. It's joules times seconds. And so when we use that in an equation, we know that energy is equal to Planck's constant times frequency. So frequency and energy are directly related to each other. So as we go to solve problem number 11 now, where we're calculating the energy of a photon of radiation, that's this equation here. So I'm looking for energy. I know Planck's constant, 6.626 times 10 to the negative 34th joules times seconds. And I'm going to plug in frequency here of 8.5 times 10 to the 14th waves per second. So when I do that, I see right away that the seconds are going to cancel, and the unit that remains is going to be joules. And so solving that, I get that the energy is equal to 5.63 times 10 to the negative 19th joules. Now, technically, that is joules per photon. And I know that might be a little confusing because it doesn't really appear anywhere in the equation. But anytime you're using this equation, it is for the energy of a photon. And a photon is just a particle of light. So problem 12 now, that again is that energy is equal to Planck's constant times frequency. We're looking for energy again, so that's going to be 6.626 times 10 to the negative 34th joules times seconds. And we're going to multiply that by the frequency, 5.02 times 10 to the 20th hertz. And we're going to get that that is 3.33 times 10 to the negative 13th joules per photon. Now, this next problem is a little more challenging because this time we're looking for energy still, but we're given the wavelength, not the frequency. So the first thing we have to do in problem 13 is we've got to convert the wavelength to frequency. Well, we know how to do that. The speed of light is equal to the wavelength times the frequency. So if I'm solving for frequency, right, then c over lambda is equal to frequency. So I know that's going to be 3 times 10 to the 8th over the wavelength of 6.4 times 10 to the negative 7th meters. So I should have put the units in up here for speed, meters per second. And so when I do that and punch this into my calculator, I get that the frequency is equal to 4.69 times 10 to the 14th hertz. Now I can solve for the energy, knowing that the energy is equal to Planck's constant, 6.626 times 10 to the negative 34th joules times seconds. I'm going to multiply that by the frequency, 4.69 times 10 to the 14th hertz. And I get 3.11 times 10 to the negative 19th joules per photon.